discuss about the structure, synthesis, physical and chemical properties of alkanes. So before going to that topic, first of all, let us discuss about what are hydrocarbons. Hydrocarbons means the carbon hydrogen containing compounds are known as hydrocarbons, and the hydrocarbons are classified into two types. One is acyclic hydrocarbons and the other one is cyclic hydrocarbons. Acyclic hydrocarbons means open chain. So the carbons are straight way. The carbons are linked in a straight way. Then they are known as acyclic hydrocarbons. In cyclic hydrocarbons, the carbons are in the cyclically bonded with each other. Then they are known as cyclic hydrocarbons. So coming to the acyclic hydrocarbons, the acyclic hydrocarbons are classified into two types. One is saturated hydrocarbons and the other one is unsaturated hydrocarbons. Saturated hydrocarbons means in which all the carbons are in sp3 hybridized. In saturated hydrocarbons, the valency 4 of carbon is satisfied with 4 sigma bonds. Then the hydrocarbons are known as saturated hydrocarbons. In unsaturated hydrocarbons, the valency 4 of carbon is satisfied with both sigma and pi bonds. Then they are known as unsaturated hydrocarbons. So coming to the saturated hydrocarbons, example for saturated hydrocarbons are alkanes. So alkanes are the best example for saturated hydrocarbons, and they are the organic compounds that consist entirely is carbon single bonds and carbon hydrogen single bonds. So all are single bonds in alkanes. Then they are examples for saturated hydrocarbons, and the general formula of alkanes is CnH2n plus 2. And alkanes are subdivided into three types. One is linear straight chain alkanes, branched alkanes and cycloalkanes. And they are also called as paraffins. Alkanes are also referred as paraffins. So if the N of the general formula CnH2n plus 2 is 1, then it is named as methane. And if you remove one hydrogen from methane, we can get alkyl group methyl, which is called as methyl. And if the number of carbons is 2, then it is considered as C2H6, which is ethane. And the alkyl group which is coming from ethane is ethyl. And if 3 carbons are present, then it is known as propane. And the alkyl group which is coming from propane is propyl, and so on. Up to 10, here I wrote. So 10 carbons, then it is considered as decane, and the alkyl group coming from decane is decyl. So in alkanes, the carbon atom is in sp3 hybridization. So in alkane, all the carbons are in sp3 hybridization. Only sigma bonds are formed in alkanes. Suppose if I take ethane, 2 carbons are present in ethane and each carbon is in sp3 hybridization. So the shape of alkanes is tetrahedral in shape, and the Cc sigma bonds present in alkanes and also CH sigma bonds are also present in alkanes, and the Cc sigma bond length in alkanes is 1.54 angstroms. But in the case of unsaturated hydrocarbons, the valency 4 of carbon is satisfied with both sigma and pi bonds. Example for unsaturated hydrocarbons is alkenes and alkynes. In alkenes, the carbon is in sp2 hybridization, and in alkynes, the carbon is in sp hybridization. But in alkanes, the carbon is in sp3 hybridization. See, in alkanes, there are 4 types of carbons are present. One is primary carbon, which is attached to only one carbon. See, this is primary carbon and this is attached to only one carbon. If the carbon is attached to 2 more carbons, see, secondary carbon, it is considered as secondary carbon. If the carbon is attached to 3 carbons, 1, 2, 3 carbons, then that carbon is considered as tertiary carbon. If the carbon is attached to 4 carbons, suppose if take this carbon, it is attached to 4 carbons, then that carbon is considered as quaternary carbon. So there are 4 types of carbons may be present in alkanes: primary carbon, which is attached to only one carbon; secondary carbon, which has 2 neighbor carbons; tertiary carbon, which has 3 neighbor carbons; quaternary carbon which has 4 neighbor carbons. So coming to the preparation of alkanes, how can we prepare alkanes? Number of methods are existing for the preparation of alkanes. Among them, the most important one is Wurtz reaction. So it is an organic chemical reaction, coupling reaction, in which the sodium metal is reacted with the 2 alkyl halides in the presence of dry ether to form higher alkanes along with a compound containing sodium and halogen. Suppose if I take alkyl halides, the reaction of alkyl halides with sodium metal in the presence of dry ether, we can get higher alkanes, and coupling between the 2 alkyl groups takes place and gives higher alkanes. Suppose if I take methyl halide, the reaction of methyl halide with sodium metal in the presence of dry ether, the coupling between the 2 methyl groups takes place and we can get ethane. Example of Wurtz reaction, suppose if I take methyl chloride, see here it is a methyl chloride, this on treatment with sodium metal in the presence of dry ether, the coupling between the 2 methyl groups takes place and gives ethane. So in that way we can prepare higher alkanes by using Wurtz reaction. And another important reaction for the preparation of alkanes is Wurtz-Fittig reaction. So it is a chemical reaction that takes place between aryl halides and alkyl halides. So the reaction of alkyl halides with aryl halides in the presence of sodium metal and dry ether, coupling between the alkyl group and aryl group takes place and gives substituted aryls. Alkyl substituted benzenes are obtained. With this reaction, we can prepare substituted benzenes. Suppose here, suppose if I take methyl bromide, which on treatment with bromobenzene in presence of sodium metal and dry ether, then the coupling between the methyl group of methyl bromide and phenyl group takes place and gives toluene or methyl benzene. And so by using this Wurtz-Fittig reaction, we can prepare substituted benzenes, alkyl substituted benzenes. And another important synthesis method for the preparation of alkanes is Coriho's synthesis. It is an organic reaction that involves the reaction of lithium dialkyl cuprates. See, lithium dialkyl cuprates with alkyl halides. The coupling between the alkyl group of alkyl halide and the alkyl group of lithium dialkyl cuprate takes place and gives higher alkanes. Lithium dialkyl cuprate is also considered as K.B.N reagent. So this method is very important and best method than the Wurtz reaction. Here the coupling takes place between the alkyl group of alkyl halide and the alkyl group of lithium dialkyl cuprate and gives higher alkanes. See, here R and R dash may be or same or may not be same. They may also be different. Suppose if I take isopropyl bromide, this on treatment with lithium, then I can get lithium diisopropyl cuprate. Lithium diisopropyl cuprate is obtained, and the reaction of this lithium diisopropyl cuprate with N-propyl bromide. The coupling between the isopropyl group and N-propyl group takes place and gives N-methyl pentane or isohexane. See, isohexane is obtained. Here the coupling takes place between N-propyl group of bromopropane and the isopropyl group of K.B.N reagent and gives the corresponding alkane, higher alkane, that is N-methyl pentane or isohexane. So in this, how the K.B.N reagent is prepared? So the preparation of K.B.N reagent takes place in 2 steps. First, alkyl halides react with lithium and gives alkyl lithiums in the first step, and this alkyl lithium react with cuprosides. Cuprosides are copperided and gives lithium dialkyl cuprate, and this lithium dialkyl cuprate reacts with alkyl halides and gives higher alkanes by the coupling reaction that takes place between lithium dialkyl cuprates and alkyl halides, and we can get higher alkanes. So this is the most important synthesis and which is better method than the Wurtz reaction for the preparation of alkanes. So coming to the physical and chemical properties of alkanes, generally alkanes have no color, they are colorless compounds, alkanes are, and alkanes dissolve more readily in non-polar solvents because they are non-polar. As alkanes are non-polar, they are readily soluble in non-polar solvents, but insoluble in polar solvents. So, and they do not dissolve in water because they are non-polar. Since alkanes are non-polar, they are not soluble in polar solvents like water. That's why they are not soluble in water. And the melting and boiling temperatures of the short chain alkanes are low, but with increasing the number of carbons, the melting and boiling points also increases in the carbon chain rises. And coming to the chemical properties of alkanes, as alkanes are considered as paraffins because they are relatively unreactive. Most of the alkanes are less reactive because they are saturated compounds. They are less reactive as compared to the unsaturated compounds. Since alkanes are saturated, they are less reactive when compared to the unsaturated compounds. So they have less chemical reactivity, and in all the carbon atoms of alkanes are sp3 hybridized, that means saturated. The general electronic configuration, the general configuration of alkanes is CnH2n plus 2, and they are tetrahedral in geometry, and the bond angle is 109 degrees 47 minutes. Since they are unreactive, but sometimes they are participating in free radical substitution reactions in the presence of light. Alkanes are generally participating in free radical substitution reactions in the presence of light. So suppose if I take methane in the presence of light on treatment with chlorine, it gives carbon tetrachloride in series of steps or series of reactions. See, methane here, methane on treatment with chlorine in the presence of light, we can get chloromethane plus HCl. That means the hydrogen atom of methane is substituted by chlorine and gives chloromethane plus HCl. So this is the free radical substitution reaction that takes place in alkanes. That is halogenation, and it takes place through a chain mechanism. The substitution reactions or the halogenation reaction that takes place in alkanes takes place through the chain process, and it takes place through a free radical chain mechanism, and it takes place in the free radical chain mechanism involves 3 steps. One is chain initiation process, chain termination process, and chain propagation process. So the free radical chain mechanism that takes place in alkanes involves 3 steps mainly: initiation, propagation, and termination. Suppose if I take methane, this on treatment with chlorine, it gives methyl chloride plus HCl, and methyl chloride again react with another molecule of chlorine and gives methylene chloride plus HCl, and also methylene chloride again react with another molecule of chlorine and gives chloroform plus HCl. Again chloroform react with another molecule of chlorine and gives carbon tetrachloride and HCl. See how the mechanism takes place. It takes place in, as I said earlier, that it takes place in 3 steps. So the first step is the homolytic cleavage of chlorine into chlorine radicals in the presence of light. So the homolytic cleavage of chlorine molecule into 2 chlorine atoms or chlorine free radicals takes place, and which is initiated by light, or in the presence of light this homolytic process is initiated. Since see, chlorine in the presence of light, the homolytic cleavage of the chlorine takes place and gives chlorine radicals or chlorine atoms. Homolytic cleavage means the cleavage of bond takes place with equal sharing of electrons. The bond cleavage or bond breaking between the 2 atoms takes place with the equal sharing of electrons is known as homolytic cleavage, and this homolytic cleavage generally takes place in the presence of light and results free radicals. So homolytic cleavage of chlorine molecule gives chlorine radicals. This is the chain propagation step, chain termination step. And coming to the chain propagation step, the free radical, the chlorine free radical which is obtained in the initiation step, this is the chain initiation step, and the chlorine free radical which is obtained in the chain initiation step reacts with the molecule of methane and abstracts a hydrogen from the methane. This chlorine radical abstracts hydrogen from the methane and gives methyl radical plus HCl. Then this methyl radical react with the chlorine molecule, and this methyl radical abstracts chlorine from the chlorine molecule and gives methyl chloride or chloromethane plus chlorine radical. So by this way these 2 steps takes place in a series. After then we can get carbon tetrachloride. So this methyl chloromethane Again, it reacts with this chlorine radical, and this chlorine radical abstracts hydrogen from the methyl radical. See, methyl radical and chlorine. By this way, after undergoing series of steps, finally we get carbon tetrachloride in this chain propagation step. So coming to the chain termination step, how the reaction terminates. So in the chain termination step, the free radical substitution reaction terminates by the combination of two chlorine radicals, or by coupling of two chlorine radicals to give chlorine molecule, or by coupling of one methyl radical with the chlorine radical to give chloromethane, or by coupling of two methyl radicals to give ethane. So by undergoing these three coupling reactions, the radical reaction may terminates. So in the free radical substitution reaction of alkanes, it takes place in three steps. One is initiation step, second one is propagation step, and third one is termination step. So in the termination step, the reaction stops. Okay, thank you.